Very good day, everyone. My name is teacher Davenzeos, a Bachelor of Aerospace Engineering from University Putra, Malaysia. So, for our Engineering Mathematic 1 class, we were tasked to come up with a project that relate the calculus with coronavirus. So, how we want to understand that, we can see it from this project. So, basically, the title of my project is Unveiling the Magic of Calculus, where we use the skill of our skill on in calculus to understand the outbreak of coronavirus. So we will learn that mathematics is not only calculating bills or counting stuff. We can use the knowledge as well in understanding and even simulate the infections within the population. Moving on into our introduction. So in this writing, there will be a mathematical model that we need so that we can use this mathematical model to simulate the infections within the population. And in this model, we need to group the population into three groups. Basically, the whole population will be denoted as N, where it represents the population of people, whereas more part of it is infected with the virus. In this N group, we have susceptible group, those that might spread the virus to non-infected people. And we also have infected group, denoted as I, where it represents those that infected and might spread the disease. And we even have the removed group, the group of people that are resistant to the disease or might have recovered or might have died as well. With that being said, we have the first formula where the sum of S group passed by I group and R group and I group will be equivalent to the whole population. The next part of the presentation is explanation of the methodology, basically how the steps that are required in our SAR model or maybe our mathematical model. So the first step is to identify the required function in order to find the rate of change of the disease. So we need contact rate that will be denoted as constant beta here, and the rate of infection is actually dependent on this beta multiplied with the size of group infected group multiplied with the size of group S. So that's how we going to find the general formula for rate of infection. But then we still have but what we want is to find the rate of change for each group. That's why we will need another constant, which is known as gamma here, where it will represent the recovery rate. So basically, we will have our first three equations where resembles the rate of increase for each group. So basically, like how the increase of susceptible group will be represented by this formula and so on. Okay, the next part of the methodology is by finding the function of time. So we know that these groups will change from time to time. So we can say that these groups are function of time. So this is kind of familiar way of denote all these functions. So that's why we need t as a finite change of time to complete our function. And we will also have data t that will be defined as 1 day and this little t here as today. So we need this to complete our function. But making use of this term, yesterday can be defined as t minus data t. So and vice versa means that t plus data t will represent the next day. So what this function means here is we can find the size of the rate of change for each group the next day by using this formula here. The next part of methodology is to find the derivative of this function of time. So we know that this function involves change of time. We need to change it into its derivative form. So from here, if we differentiate this function, we can come up with this function. So basically, this function represents the rate of change for the next day, each day. So the next step in our method is to find the integration of this function. Why we need to integrate this? Because in this derivative form, it is actually represent the rate of change. But what we want to find is not the rate of change. What we need in our SR model is actually the size of the group in the next day, not the rate of change. That's why we need to integrate it. So that's why we use Euler integration. It is an explicit integration method. Means that the state of a system at a later time is calculated from the state of the system at the current time. So basically, in our case, the state of our model tomorrow is calculated based on the state of our model today. So we will have when we integrate this function, it turns out like this function of time here again. But to make things easier in our SR model, since we need this formula later to compute the values, that's why we're gonna denote instead of using t here, we're gonna use I to indicate the number of days. So that how we come up with this function. The last part in the methodology is computing the values for our SIR model. So by using this integrated function, we can create our own SIR model to simulate the infection of the virus. So in the making of our SIR model, we can find the number of the population in each group by substituting reasonable values in the function. So what are those constants that are required? So if you can see these two constant here, beta and gamma, actually plays a major role in this our SR model later on. So also in our case, going to try our best to relate it based on our situation currently. Since we've done with the methodology, now let's go to the result and discussion. So basically, the result which shows like what our model is. So here you can see that to come up with this SR model, there are some parameters have been set beforehand. So we assume that only 0.1% of the population has been infected by the disease on day zero. So we also have an assumption that the change in a day, so basically delta t, as 1, whereby the infection rate beta as 0.6 and the recovery rate gamma as zero point 0.1. So by using the integrated function just now, we managed to compute the amount of people in each group per day. So the SR model here simulates how each group affect the other for 30 days. As the amount of infected people increases, we can see the amount of susceptible people are decreasing at the same time. Those susceptible people are no longer in the susceptible group because they have been infected by the disease. So in other words, or to summarize it, size of infected group has been fluctuating, whereby the susceptible group decrease, and the removed group increase as time goes on. But this is another way to show a situation that is not currently yet in our country, where the recovery rate exceeds the infection rate. So you can see it here. The figure simulates a situation where the infection rate here, beta, is lower than the recovery rate, gamma. For this model, we use the infection rate as a beta is 0.4, whereby the recovery rate, gamma, is 0.5. You can see the graph is stagnant for 50 days. So basically, the ability to recover from the disease has exceeded the infection rate. The amount of infected people is the same as removed people, where it remains at 0. So the next part of the result and discussion is flatten the curve. This is quite an interesting finding during this throughout this project. So what is this flatten the curve actually is? So during the early phase of COVID-19, this flattening the curve was a public health approach to reduce the spread of the virus. And this flatten the curve entails slowing the spread of the epidemic so that the peak number of people in need of care at any given moment is lower than the healthcare system, so that the healthcare system is not overburdened. This flattening curve can be used as a representation for the effectiveness of government's countermeasure. There were few population that strongly against the idea of lockdown, social distancing, and even wearing face masks. These people thought that the government has snatched their freedom by doing so. With this flattening curve being made, it can be a solid proof that helped in increasing the public awareness on how dire the situation was. So that's what quite an interesting thing, because we have some people that strongly against the idea of lockdown, wearing masks, social distancing. We can use this flatten the curve to show them that the countermeasures made by the government is mathematically proven, valid, and legit. Here is how we simulate the flatten the curve by using the same formula that we have integrated before. So we have here is the graph that represents the situation when there is no prevention against the disease. So we can see the infected group increase and all the susceptible individuals fall into the infected group. In other words, all population in the world has been infected by the virus. This situation shows the outbreak has exceeded the capacity of our healthcare system. So we made a few assumptions here as well. Since that no, there is no prevention, we can assume the recovery rate is 0, and this is what happens afterwards for the next 30 days. The next part of the flatten the curve is a graph that represents the situation when there is a prevention against the disease. So the recovery rate is not zero anymore. This prevention can be social distancing, sanitation, and lockdown. You can see the infected group here starts to dip after 20 days, and the graph starts to flatten a bit due to the countermeasure. So, in other words, our healthcare system will be able to contain the disease and increase the recovery rate as time goes by. Even if the infected people increases, the recovery rate will always increasing, just as represented here. Another part that I want to emphasize here is something that we know as basic reproduction number. So what is this basic reproduction number actually? It is denoted as R naught, where the infection rate divided by recovery rate, which means in our case beta divided by gamma. So based on our SR model, our R naught is bigger than 1, and we can use our result to represent a situation we are going through currently. This happened because the infection rate is bigger than the recovery rate, and it caused the graph for infected people to fluctuate. If this situation remains, we'll never be able to achieve COVID-free life that we used to have. In other words, it is important to keep R naught below than 1. So when R naught is below than 1, the result will be different, where the amount of infected will never exceed the amount recovered. This will put down the pandemic in a situation where our healthcare system is not overburdened. Just like the graph here, this is what the graph will look like when the R naught, the basic reproduction number is lower than 1. So it will indicate that our recovery rate during the pandemic is bigger than the infection rate. So what it will looks like when the R naught is bigger than 1. Basically, this is our situation right now. It indicates the recovery rate where it is lower than the infection rate. If this situation prolongs, our healthcare system will be put in danger as well as our safety. In addition to that, the outbreak of the disease will be uncontrollable for the next days. Moving on to the last part of result and discussion, which is the preventions of COVID-19. Our government has implemented various countermeasures to prevent further spread of the disease, such as wearing masks and social distancing. COVID-19 spreads for infected people to susceptible people mainly through respiratory droplets. So that's why we need to wear masks. Masks work simply as a barrier to help preventing the respiratory droplets from reaching others, whereby the social distancing, on the other hand, helps in decreasing the number of contacts between these groups. When there is less contact, there will be less chance of this virus to transmit to others. This measure will affect the infection rate because the number of contacts will be decreased and the transmissibility will also decrease. The next one is disinfection. So basically, like we can apply this in our own household, where regular household disinfection products is is works in eliminating the virus from household surfaces. So we have come into the last part of the project, which is the conclusion. So to conclude everything we have so far, we use our knowledge on derivative of function as well as integration to come up with our mathematical model. So we use differentiation, and we managed to come out with the functions representing the rate of change of each group, susceptible group, infected group, and even removed group. However, our SR model required the number of people in each group rather than the rate of change for these groups. In this case, we used our skill in integration, and we also came up with functions that we use to compute the values for our SR model. So by using these two powerful mathematics skills, we also managed to identify like how these protective measures affect the infection rate, how it works with the flatten the curve, how how actually the measures that are enforced by the government is actually helping the public and in even the whole population. So for a short reflection, it is quite scary that how fast this disease managed to spread in a short period of time, and how hard it is to maintain the affected group remain below the health system capacity, so that we so it is scary if it exceeds and we have no chance anymore to make things right again. So that's all from me. Thank you.